Okay, so let's get right into it. We're going to be talking about a revolutionary new supercomputer. But look, this isn't just about making something a little bit faster. This is about a machine that, well, it thinks in a fundamentally different way. And that way could honestly change everything we know about computing. Think about it. From the smartphone in your hand to the most powerful server farms on the planet, they all share the exact same basic design. And that design, which is now over 70 years old, has a massive built-in bottleneck. And it's holding back the true potential of AI. So you have to ask a pretty radical question, right? What if, for the last 7 decades, we've been building our thinking machines completely the wrong way? What if the real answer isn't just more raw power, but a totally different blueprint? All right, so to really get why this new machine is such a breakthrough, we first have to understand the problem it's trying to solve. And it all goes back to this 70-year-old bottleneck and how basically every computer is structured. This slide just nails the issue perfectly. On the left, you've got the old way, the von Neumann architecture. The processor, the brain, and the memory are in 2 different places. This means data is constantly being shuttled back and forth, creating this massive digital traffic jam. But now look at the right. That's how your brain does it. In a real neuron, the processing and the memory are all mixed together in the same spot. There's no shuttle, no traffic jam. It is just radically more efficient. And that incredible efficiency, that genius design of the biological brain, well, that's exactly what scientists are now finally able to build in silicon. They're not just trying to program a computer to act smart anymore. They're literally building a digital brain from the ground up. Just take a look at this number for a second. Let it sink in. It is just unbelievably huge. What on earth could that possibly be? That's it. 228 trillion. That is the number of synaptic operations the new DeepSouth supercomputer can pull off every single second. And here's the real kicker. This is the first time any machine ever has hit a processing rate that actually matches the scale of the human brain. We're not talking about an approximation here. We're talking about one-to-one simulation speed. So how does it pull this off? Well, the magic is in something called spiking neural networks. You see, unlike the AI we're used to now, which is always on, always crunching numbers, SNNs work a lot more like our own brains. The neurons just sit there quietly, using almost no energy, until, bam, they get enough input to fire off a signal. In this system, silence isn't just golden, it's efficiency. And that incredible efficiency leads us to what is maybe the most jaw-dropping part of this whole story. It's absurdly low power consumption. I mean, this chart just says it all, doesn't it? It's what we can call the power paradox. Your brain, the most complex and powerful computer in the known universe, runs on just 20 watts. 20. Meanwhile, a traditional supercomputer can chew through megawatts. That's millions of watts. The difference isn't just big, it's astronomical. Let me put that in perspective for you. Your brain operates on the same amount of juice as a dim little light bulb. The massive server farms needed to train a big AI model, they can consume enough electricity to power a small city. DeepSouth is designed to finally close that absolutely insane gap. And this table here really drives the whole point home. You can just see the fundamental differences. A traditional computer is linear, constantly pulling for data, burning through megawatts. DeepSouth, on the other hand, is parallel, it's biological, it's event-driven, which makes its power use incredibly low. They're built for totally different jobs. One is for super precise math, and the other is for recognizing patterns, just like a brain. Okay, so we get what DeepSouth is. Now for the big question, what is it actually for? Well, the researchers who build it see its impact coming in 3 distinct waves, or what they call horizons. So Horizon 1 is the most immediate, and it's huge for medicine. DeepSouth is going to act as a biological mirror. For the very first time, neuroscientists can build a full-scale digital twin of the human brain. They can simulate diseases like Alzheimer's or Parkinson's, not just by looking at symptoms, but by modeling them at the synaptic level. We're going from just observing the brain to actually being able to debug it. All right, Horizon 2 is where we start to shrink this technology down. Imagine a tiny, powerful AI chip on a drone that can navigate a dense forest all by itself without ever needing to connect to the cloud, and it can run for days on a tiny battery. Or think about advanced prosthetics that can interpret brain signals in real time. This is the future of smart, low-power devices out in the real world. And then there's the long-term horizon, the big one. You see, current AI is amazing, but it's very narrow.
It can't learn and adapt with the kind of general intelligence that a human toddler has. The hope here is that by perfectly mimicking the brain's actual physical structure, DeepSouth could become the cradle for a totally new kind of emergent intelligence. The kind of spontaneous learning that might, just might, lead us to artificial general intelligence, or AGI.
You know, a technological leap this big doesn't just raise questions about computers and AI. It forces us to look in the mirror and confront some of the deepest philosophical questions about, well, about us. And this is really the question that's going to define the next century of this research, isn't it? If you build a machine that is a one-to-one copy of a human brain, structurally, functionally, at what point does it stop being just a simulation? At what point does that amazing collection of silicon and circuits cross some invisible line from just processing data to something more? In the end, I think the team behind DeepSouth put it best. They said, we aren't just building a faster computer, we are finally building a mirror. And what we see when we look into that reflection, all the potential, all the power, and all the profound questions about our own consciousness, that's what makes this one of the most exciting scientific frontiers of our lifetime.